When a fault strikes, the protection system has only milliseconds to act, and it all starts with the instrument transformer. In this video, we will explore how protection CTs are classified, and what markings like 5P, PS, TPX, or TPY tell us about their performance. But first, a quick note on specifying CTs. Regardless of class, always consider rated currents, short time and dynamic current ratings, number of cores, insulation level, ambient temperature, and other application-specific requirements. Now, let's look at the three classification approaches defined in IEC 61869 for protection CTs. The first approach is to define CTs to meet composite error requirements under steady-state, symmetrical short-circuit current. This is the most traditional method. It includes the widely used Class P and Class PR CTs. This class of CT is typically used in overcurrent protection. These are defined using three key parameters. Accuracy class, 5P or 10P. Accuracy limit factor. Rated burden. You have probably seen CTs marked as 15 VA, 5P20 or 10P20. Let's break that down. The 15 VA in this case is the rated burden, which tells you how much load in volt-amps the CT is designed to drive at its specified accuracy. The number before the letter P, like 5 or 10, indicates the maximum allowable composite error in percent. The letter P stands for protection. The number after P, like 20, is the accuracy limit factor, or ALF. ALF defines the multiple of rated primary current up to which the CT maintains its specified accuracy, assuming the rated burden is connected. For example, 5P20 means the CT has 5% maximum composite error up to 20 times rated current. Standard ALF values include 5, 10, 15, 20, and 30. Now, what about Class PR? Class PR CTs follow the same three-parameter definition as Class P, but with one important addition. Class PR CTs must maintain remanence below 10%. To achieve this, air gaps are introduced into the magnetic core to reduce residual magnetism after a fault. The second approach defines CTs based on their magnetizing characteristics under steady-state, symmetrical short-circuit current. This approach defines CTs like Class PX, or PS, and Class PXR. This type of CT is often used in current balance protection scheme like differential or REF protection. These CTs are defined by the following parameters. Knee point voltage. The voltage at which a 10% increase in voltage causes a 50% increase in excitation current, indicating the onset of core saturation. Excitation current at a specified percentage of knee point voltage. Secondary winding resistance, RCT. For example, you might define a Class PS CT to have a knee point voltage of 400 volt, an excitation current of less than 30 mA for a 1 amp CT, or 150 mA for a 5 amp CT at half a VK. A specific secondary winding resistance, such as 1.2 ohms. Instead of specifying the knee point voltage explicitly, it may be specified with this equation. In such cases, the rated burden, RB, and dimensioning factor, KX, or rated symmetrical short-circuit current factor are specified, and the manufacturer decides the winding resistance. This gives the manufacturer flexibility to choose RCT appropriately, helping avoid oversizing and keeping the CT economical. Like Class PR, Class PXR CTs must also maintain remanence below 10%, often by incorporating air gaps in the core. The third approach is to define CTs to meet transient error requirements during asymmetrical faults. That is when a large DC offset is present. Modern relays often operate very quickly, often before the transient settles. During this time, CTs may saturate, risking relay misoperation. To handle this, Class TPX, TPY, or TPZ CT is used. This is a complex and important topic, and we will cover it thoroughly in the next video. So, we will pause here for now. But before that, let's summarize what we learned today. As per IEC 61869, protection class CTs are classified using three distinct approaches. The P and PR class CTs are defined based on composite error under steady state, symmetrical short circuit current. The PX, or PS, and PXR class CTs are defined based on magnetizing characteristics under the same steady state conditions. For this type of CTs, manufacturers may be given flexibility in choosing RCT, allowing for optimized CT design. The TPX, TPY, and TPZ class CTs are defined based on transient error during asymmetrical short circuit currents, which will be covered in detail in the next video. The requirement of remanence below 10% is often achieved with air-gapped cores. While these classification methods differ in how performance is defined, they may still result in the same physical CT design. What matters most is choosing the classification that matches your protection requirements. That's it for today. Thanks for watching, and see you in the next part.